Good morning to all. Am I audible, Mr. Mehul?
Yes, sir, you are audible, sir, perfectly.
Okay, okay. So we have right now the session on digitalization, the next steps towards enhanced energy efficiency. And we have speakers from uh, India and abroad in this session. And uh, on this subject, I'd like to say a few words that one of the major challenges today is the flexible operation in view of the RE expansion in our country. And in fact, it is the scenario world over. How to equip our plants for being able to adapt to the demand changes, the machine capabilities, the optimal operating regime, and the reliability. These are some of the challenges that we need to address. And also, the major element in the power generation, the people, that also needs to be taken care of and to be trained for the latest changes and be capable of handling these issues. And for that, a simulator based approach for training will be very important. And in this, the digital twin technologies can also play a great role. In fact, my vision will be that now onwards that all the manufacturers, the OEMs, they should be, giving it as a integral part of the package, the simulators for the machine they are supplying. Now, what are the technologies available for bringing down the carbon footprint? That is another aspect, and digitalization can play a great role in that too. So we have to look at, are we geared up enough to retain the millennials also in the power industry who are quite IT savvy and would look forward to the controls and operations based on the digital technology. Now, on this note, I would like to, invite our learned speaker, Mr. Rajbhar KR from Global, who is the Global Business Head for TCS IP2. He is going to talk on digital twin for performance enhancement. So, may I invite Mr. Rajbhar KR?
Thank you, Mr. Pankaj. Hope I'm audible and visible.
Yes, you are.
Thank you so much. At the outset, I take this opportunity to thank CII, Godrej Business Center, for giving us this opportunity. And let me introduce myself. I'm Raj Bharat. You can call me Raj. I head global business for TCS IP2 solution from Tata Consultancy Services, and we primarily deal with in the area of thermal power generation sector. And today, my intention is to walk you through a case study from Japan of how the customer has been able to enable AI guided decision making in the power plants with digital twin technology. So that is what we will talk about. But before we even get started, I think to take a moment and acknowledge CII for doing this initiative, because we're all bound to our desks these days because of work from home. And it's really truly liberating to have such a conference and synergize your thoughts across the industry. From that perspective, our sincere thanks goes to CII. And like Mr. Pankaj rightly remarked in yesterday's session, the essential part of all ecosystem players coming together. And just like the president of DB Power also remarked, each ecosystem player has a responsibility. And as a technology provider, it is our responsibility to bring the technology which enables the end user and the OEM to, realize the true realities. And for thermal plants to be the big brother in the entire ecosystem with over 70% of capacity as it is today, I think we need some radical changes but these changes need not be at the cost of removing existing systems. So that is the key message I want to start with. And essentially, let me share my screen as well. Yeah. And essentially, with the intention of an Atmanirbhar Bharat, it is also an ethical responsibility for us, being an Indian company, to provide our sectors with these technologies. With that, so today we're going to talk about AI-guided digital power plants, specifically about the ultra supercritical 1,000 megawatt plant that we had worked with in Japan. So that's going to be the core, but I'll also touch upon certain other case studies and talk about that as well. I don't want to bore you with too much content, so I'm keeping this presentation in very visual to give you a view of how, a touch and feel of how things operate. And the key thing here is driving sustainable, flexible, and market-linked operations. And that is the entire motive of what we are trying to do here. Now, we also would like to acknowledge EPRI, who is our partner. We are part of the I4Gen program. We would like to acknowledge EPRI for their contribution and wealth of knowledge, which has helped us grow from to where we are today. With that, I'll start with the first thing, which is about the key challenges faced by thermal power plant sector. I'm not going to delve into detail because we amply discussed it yesterday, but to touch upon some critical points, right? Flexible operations being one, which causes a lot of thermomechanical stress in the equipment. Enabling flexible operations is one, and optimizing plant during flexible operations is a whole different challenge. So how do we enable this? First of all, doing an assessment, like it was remarked yesterday, doing an assessment of flexible operations itself is expensive. But what if there is a low-cost digital solution that can, help with optimizing plants in flexible operations? We have one such experience in with a group company of ours in India itself. So that is something which could be handy here. Uh, and of course, referencing to the talk which Dr. Venkatramkana gave yesterday, where he talked about digital twins. So I'll take from there and give you a practical perspective of how things work in the industry, in the plant setup. Second is, of course, about emissions, NOx, SOx, carbon emissions, and 1% of carbon reduction is equivalent to 1% of efficiency improvement is equivalent to 2% reduction in carbon emissions, as some of our colleagues rightly remarked yesterday. And the point which Mr. Pankaj made just now about retaining millennials, that is definitely an important thing with India's demographic dividend. I think that is crucial. But what's also essential is retaining the knowledge base in a digital form, which can be disseminated on the one hand, and which can also be actionable for taking decisions in the power plants. How can AI guide decisions with the system knowledge from its operators? That is also essential. And finally, the biggest thing we see is barriers to digital adoption. So how can we make that easy and make operators interact with such digital systems easily without doing much of coding, without getting their hands dirty with a lot of technical things, meaning IT technical digital things, but rather interacting with a domain flavor and still being able to accomplish it. So these are the challenges which we are facing today and which we are set out to mitigate. So the story today starts with the Fukushima disaster in Japan. So the story starts there because after the disaster, Japan faced a critical challenge of shutting down all their nuclear power plants. So the thermal power plants had to take that load, and they've had to have highest levels of efficiency and reliability. So the customer whom we worked with also face this challenge because they are the biggest thermal producers in Japan with over 67 gigawatt of capacity, largely from coal-based operations. Now, the challenge they faced, we worked with them and we created a three-stage journey, which is what we recommend to the industry as well for digitization. So digitization cannot be accomplished in day one. So we have look at it in three phases. We can call it connect, predict, and self-aware. These are the three phases we can look at, or in simpler terms, first stage is digitization, second is semi-autonomous operation, and third could be autonomous operations, where it's not completely autonomous, whereas different systems and subsystems are able to operate in autonomous conditions. So this is the maturity which we have to look at, and each one is a precursor to the previous one. So it is important that we adopt this maturity model. If not, it would be difficult to leapfrog right away to digital power plant. So that is the first thing. So now here we have been able to implement a lot of use cases in their supercritical power plant, such as combustion optimization, asset and process fault tree analysis, failure mode effect analysis, prediction of coal properties. This was also remarked earlier, where it's very difficult, identify what coal the plant is operating on right now. So is there a way to predict these coal properties? So we'll talk about that as well. Prediction of ash softening point or ash fusion point to prevent fouling in your superheater zones, and reducing emissions, your NOx emission, predictive maintenance of your assets. So these are the things which we have implemented for this customer. So we will show you how it looks and feels with respect to that. And we've been fortunate enough to realize benefits to the tune of 8% reduction in NOx, reduction in unburned carbon to the tune of 1.5%, improvement in boiler efficiency to the tune of 0.5%, and overall $2 million in savings. So now the first question is, when we say AI guided operations or AI guided decision making, as we are talking about, what happens? How does it look like in a plant? So that is the first question that comes to our mind. So here, look at this in two layers. The top layer is the physical plant, where you have a plant controlled by a control system, your DCS, and the bottom you have a digital replica or the digital twin setup, and that is where TCS IP2 intelligent power plant comes in, which I'll talk about subsequently. So we have a digital replica at the bottom, which basically feeds on the real-time information, be it your KPIs and process parameters from the plant. It assimilates this information, a lot of data, and we adopt a hybrid approach, that is thermodynamics plus data-based models. Majority is data-based models, because we understand that there could be challenges in having the design files ready, design data available for legacy plans. So why not reconstruct that with a pure data science approach, of course, guided by the domain knowledge. So that is the approach that we have taken. So coming back here, so we take the data, we get the KPIs into a system which does data pre-processing, prediction, and optimization. And these are powered by multiple asset and process twins for your each process cycle, air cycle, water cycle, flue gas cycle, each major assets like a boiler, turbine, generator, and so on, and all of them integrated together as a plant twin. So that is the core of what we do. And these digital twins and an assimilated model of these digital twins enable the AI-based decision making. So you get the KPIs, and the processing happens here, and this system rests on a data link, or it can also be on-premise system. And what it basically does is, first let us look at this loop. First, what it does is it looks at the different fixed parameters, or rather the disturbance variables, the conditions in which you have to operate, and the constraints, safety-related constraints such as metal temperature, combustion temperature, and so on. So constraints, fixed parameters, it keeps that in mind, looks at the current operating condition, and looks at particular objectives. So the objectives here could be, reducing fuel consumption, reducing NOx, improving condenser vacuum. It could be different individual objectives or a combination of objectives. Improve my combustion, at the same time keep my NOx within limits. So such combination of objectives, or different modes of operation. So I want in a low NOx mode, I want in a high efficiency mode. So all that can be defined. So different modes of operation, multiple objectives, or a singular objective, it takes into this. It does the processing and gives the set point recommendation, which goes to a plant operator, who in turn would set it to a control system. So this is how the loop goes. There is still operator here. It is not a complete closed loop control. What we do, it's an advisory system. But whereas we are also experimenting now with a full closed loop control with adaptive predictive control system here, which would sit alongside DCS and do the implementation to make it completely closed loop. So that's something which we are working on. So this is the process side. On the monitoring side, if you see, because the system has complete knowledge of the physical setup, it is also able to provide KPIs, PPIs, monitoring, different kinds of simulations, heat rate simulations, what-if analysis, and better diagnostics, FMEA-based process diagnostic. It's able to do that, and which can be consumed by the control room operator. On the maintenance side, we are able to do asset FMEA, do root cause analysis of failures, estimate asset health, predict failures before they occur, and also provide maintenance recommendation. This is how this entire digital system is providing AI-based decision support for the operator. But what is important is this AI system has to be current because the models could become obsolete after some time. So the way the technique which we have adopted is a self-tuning technique where the data is constantly the models are constantly self-tuned with the latest sets of data. So now, to give you a view of what is TCS Intelligent Power Plant, which is the solution which was used for this case study that we implemented in Japan. So a quick view of that. Here, the bottom layers you see in blue are customers' ecosystem or the plant ecosystem, where they have a plant layer, control layer, and enterprise layer. Starting from enterprise layer, TCS IP2 starts. It interfaces with the historian, with the EAM system to collect the data. And from there are four modules: IP2 Insight, IP2 Optimizer, IP2 Asset Performance Management, and IP2 Studio, which basically does all the thinking and AI decision support, which in turn gives this AI decisions to the different stakeholders within a power plant. So this is how it is entirely structured. Now, if you look at Insight, what Insight does is it gives real-time insights into operation. It has soft sensor capabilities like I was talking about, what-if analysis, doing different types of diagnostics, and all of this without any coding. It's like a simple drag and drop kind of a mechanism. So operators don't have time to do all of coding and sequencing in a plant setup. So how can that be made easy? That is the first thing. Second is from optimizer perspective. This is where set point recommendations happen. So I'll give you a quick, I'll talk about how that works subsequently. And here again, we see heat rate simulation also part of this optimizer and set point recommendation, like I said. And APM is all about asset health, managing asset health and estimating remaining useful life. And finally, we have IP2 Studio, which is responsible for managing the models. The key here is, like I mentioned earlier, breaking the digital barrier. So for us to break the digital barrier, we want the millennials who are operating a power plant, people in control room, to start building models, to start, contributing to the intelligence. How can they do that without learning Python or complex coding? They can do that with a good workbench where they can create and manage their own AI models, create and manage their own FMEA trees, and create and manage their own use cases. So that is what we are enabling with IP2 Studio. So this covers what we do in TCS Intelligent Power Plant. Now let's look at what are all the specific opportunities where AI decision support can be handy. Now again, I want to touch upon what Mr. Pankaj told yesterday about technology, people, systems, and practices being very key to bring a holistic improvement in a power plant. And we completely acknowledge that. So it's not just technology, it's also about how people interact with systems. It's also about what kind of best practices and SOPs we have in monitoring and operating a plant. Because today, because of flexible operations, there are plants changing the load of 20 to 30 or 40 times a day, and it constantly changes. With automatic generation control, it's even more frequent. So the decisions that need to be taken are very quick decisions. They need to be much more accurate. They need to be first time right. So with such amount of difficulty in taking the decisions and high stakes for the decisions, I think we can take the aid of AI in helping us with this decision support. That is the whole concept of AI-based decision making. I'm also reminded of a corporate leader's famous remark: "In God we trust. Others bring data to the table." So that's where AI and data come together and help us with the decision making. So which are the areas? So these are the areas which we're going to look at today. First is insights into operations. Second is diagnostics of anomalies. Third is prediction of failures. Fourth is optimization of processes, evaluation of scenarios. That one is interesting. And finally, discovering new value opportunities. So these are the areas which we are going to look at. Now let me go one by one. The first one that we're going to look at is the use case of coal properties prediction, which we implemented. So the customer had a typical problem, which is case for everybody. So in this case of the Japanese customer, what they felt is they do not know on which coal the plant is operating. And by the time they get the lab analysis results, it's too late. So they wanted a reverse engineering mechanism. Indians are very good with reverse engineering. So they wanted a reverse engineering mechanism where they wanted to find out the coal properties using prediction. So what we did is we developed a soft sensor where we take the current process parameters and we predicted the coal properties in real time. So the ones that you see here in cyan color, those are the predicted coal properties, whereas the one in gray are the properties, coal properties provided by the vendor. As you can see, in most of the cases, it's very close when we did a post-factor comparison. So here, these core properties are predicted. So that is the first important use case. But the next important use case is a soft sensor, again, for predicting the tertiary superheater outlet temperature. So here again, the temperatures that you see here in cyan, these are not from sensors. These are predicted values from soft sensors. So here what we do, this is again essential because to prevent.
Mr. Rajbhar, could you now please try to conclude?
Oh, okay. Sorry, I was just getting started. Fine. So we this is something which we had done, and prediction of ash softening point. So that was also something which we had implemented. Now, the second important thing is the diagnostics of anomalies. So here, this is an FMEA, failure mode effect analysis, where we do a root cause of different problems occurring in a power plant, starting with heat rate loss. So heat rate loss, the next, what causes heat rate loss? So doing a root cause analysis in real time that is done with FMEA, where we understand that heat rate loss is caused due to boiler loss and condensate loss and not because of other things. Now we can go a level deeper and identify what is causing that further, which is, dry flue gas loss. In this case, boiler loss is caused due to dry flue gas loss, which in turn is because of fouling in the air heater zone. Now, again, there is a provision to go a level deeper to look at what is causing fouling in air preheater zone, and that is where the asset FMEA is initiated, where we see that this is because of APH failure, and that's further because of bearing failure and bad lubrication. This entire diagnostics is happening in real time. And now here the operator has a provision to define the conditions of each of these nodes getting triggered as well. It is for the operator to define. On the prediction of failures, this we think we talked about, where we have a provision to predict failures, estimate an asset health score at an asset level as well as at a component level. This is very handy for the customer to plan their maintenance procedures accordingly. And even at a component level, as you can see, we have been able to calculate the asset risk score, which the operators can readily use for planning their maintenance activities. On the optimization, right, this one is key, where the objective which we took here was air heater outlet gas optimization. That was the priority for them to reduce the heat rate. And here, the most important thing is they wanted to put it within certain constraints. So they can define the constraints for upper and lower limits for their set points. And within those constraints, the system runs the optimization and it gives the recommendation to the operator. As you can see here, it gives the recommendation to the operator, which can in turn be fed to the DCS system. So it's a complete optimization for a particular objective, which is reducing the air heater temperature. Uh, Next one is on evaluating the scenarios. So on evaluating the scenarios, what we see is that for you to operate plant at different loading condition, different kinds of coal, the operators can themselves, create the scenario. They can key in the values for the set points which they want to do and simulate what will be the impact on the heat rate. So this is the simulated impact on heat rate, and if it is good, they can go ahead with setting it in the plant. And finally, coming to the last thing which we talked about is discovering new value opportunities in a power plant. So here, with a single click, how can we enable the operators to have a descriptive analytics of their current system? So in this case, this is the template for boiler combustion analysis, where the operators wanted to see how the system is operating to design models accordingly. So this is what we had implemented for them. So net, these are the things which we implemented for this customer in Japan, and they've been able to realize value in terms of improving energy efficiency, number one, and also better diagnostics and knowledge retention within the power plant because of the digital interventions. And finally, in terms of the value realized, we see that anywhere from $4 to $6 billion per gigawatt of capacity. Of course, depending on the plant load factor, there is potential to realize in a power plant from different headers such as efficiency, improving saleable megawatt, reducing your auxiliary power consumption, that is reducing emissions, preventing outages, and reducing chemical consumption such as ammonia, limestone, and so on. So that brings us to the end. There are other case studies. I'm not going to take your time to talk about all of those. I think one was talked about is the Japanese customer, but there are also other cases where customers have realized this benefit in Europe, in India, in South America, and so on. So the key point I would like to conclude with is that it is important that all of us embrace digital innovation, but when, how, and why it is very important. So in choosing use cases for implementation, I would request everybody to exercise extreme caution in picking only the right use cases, which calls for an investment for an intervention. So that gives us a lot of value, and it also enables us to scale. With that, I'd like to conclude and thank you, Mr. Pankaj, and the entire CIA team for giving us this opportunity. And thank you, and I'm open for any questions.
Thank you, Mr. Rajbhar. It has been a very enlightening, case study which you have implemented, and it's really a in thing today that the AI guided, digital solutions to the plants, wherein, as you are saying that right now you are on the advisory mode, but you are very soon going to be on the control mode too, and that will be a very useful thing to see to deal with the complexities of the system. Thank you.
Thank you. Thank you.
May I now invite Mr. Jacob Tuttle and Mr. Prabhat Verma for the talk on Beyond Process Optimization, Synergizing Multiple Conflicting Operational Objectives. Mr. Jacob.
Yes, certainly. Thank you very much. I'll go ahead and get this screen shared with you all. Can you see my screen and hear my audio all right?
Yeah.
Okay, excellent. Well, first, thank you very much, Mr. Pankaj. Very glad to be here, glad to be able to speak with you all at CII. Grateful for the presentation that we just heard. It was definitely very enlightening. But as you just expressed, I want to talk a little bit about our experiences in synergizing multiple solution approaches. First, I'll provide just a little bit of background about myself. I received my doctorate degree just recently, a little over a year ago from the University of Utah. I'm in the Department of Chemical Engineering. My doctorate work was focused on one of the aspects of reality that you expressed is permeating the electrical industry, and that's this variable load. Give me just a second, I'll bring up this pointer. All my work was focused on what do we do with these power plants when they're ramping up and down minimum load to maximum load multiple times a day. This is something very common to the work that I focused on, and primarily how do we use artificial intelligence to help our power plants to be the most efficient and also emit the fewest amount of emissions while operating in this manner to enable renewable energy and the other reasons, the other factors that contribute to load following. And so with that as my background. I've had a fair amount of experience in this work, and what I want to do now is talk with you all about what we've been able to do since my doctorate work and at various sites across the United States and internationally. So some very quick introduction and background. I don't have to tell all of you, I'm sure, how complex power generation is. Not only is there a boiler and a massive fireball that we have to somehow control to generate energy to then send to a turbine. We have to manage soot throughout the system. We have to take care of the temperature of the steam within the system itself, using steam temperatures as well as other factors, other parameters in the system. Besides that, we have to manage the air that's being introduced to the system and removed from the system via flue gas. Then we have to do something with the fly ash and different emissions such as SO2, the particulate matter, all these other things that are going on. Then aside from what's going on in the actual combustion process and downstream of that, we have to do things with our fuel. So we have to take care of our pulverizers. We have to somehow properly manage the characteristics of the fuel that we're operating with. And that's something that is very difficult to do because, as you're all aware, it's constantly changing. Besides that, we have aspects like the drum, and then we have to actually control the turbine, which is at the end of the day, it's actually producing power. And then we have ancillary systems around the turbines, such as the condensers and cooling towers. There's just so much going on in these power plants that it's, the first question is, how do we control? How do we actually manage integrating all these systems? And that is the role of the DCS. The definition of the DCS is a distributed control system. And the point of that is that it distributes control of individual components, such as those I just talked about, to enhance reliability and robustness of the control system, so that each component focuses on a single piece, essentially, and it's able to be more reliable, focusing on those individual pieces, and then they communicate upwards, basically through these different levels of control, to realize overall management of the process. So if we go back and look at our power system, though, and now we want to start discussing optimization, well, that opens up a whole other list of competing and contradictory factors that we have to account for and somehow properly manage. We have the combustion itself, where there's air and fuel. We have to try to somehow have maximum combustion efficiency while also managing temperatures. There's again ash buildup that affects heat rate, and other tube metal life, degradation of the unit. There's actual temperature control using the temperators again, and aspects of combustion. We have things that we can do to optimize air management within the system. Other things on the back end of the process, emission rates, ash management for LOI and byproducts for selling that. There's things we can do also for the fuel. There's just so many different contradictory objectives that can go on inside of these systems that how do we actually optimize? How do we realize enhanced control of these processes in a way that synergizes across the system so that the entire process is overall better? And so that's really the question of the day. One of the things that's what I'm going to focus mostly on throughout the remainder of this presentation is how do we do that? And what we've introduced, what we like to phrase this as, is a new control layer within the DCS model. We call this the add-a-variant control layer. Essentially, add-a-variant means to assist, and it's an assistant to operators and to the DCS itself to enable both to maximize their own potential, while it itself is a flexible, agile component that utilizes data and artificial intelligence with the right methodology applied at the right components and the right levels across that large distributed process, so that everything can communicate with one another and it gains an overall better picture and understanding of the system. A couple of key differences between the DCS and add-a-variant control that I want to point out very quickly is that really overall the DCS's main focus is reliability and consistency. It's meant to realize the same level of control and the same procedures time and time again. It's repeatable so that we know exactly what to expect. That way it's safe and we can trust it. We don't have any issues or questions about what's going to happen in a given circumstance. That's the idea behind DCS control. But as we all know, every moment is not the same as the last. And that's where the role of add-a-variant control comes in, to be that flexible, agile component that uses understanding of previous operation and what are the current unit characteristics to adapt operation to what's happening instantaneously in this moment. And that's really the main differences, the key to why this add-a-variant control layer exists and why we try to operate there as a component above the DCS, interacting directly with the DCS so that it can fulfill its job of being safety critical, robust, repeatable control. And then add-a-variant control is what allows that synergistic optimization using advanced AI algorithms, as well as other control methodologies. So how do we actually realize this add-a-variant control? Again, just real briefly, the idea of add-a-variant control is to be an assistant. It's really a bridge between operators and humans and machines, so that they both can maximize their own potential. And a key component of it is that it's designed to implement the right tool for the right job, meaning that sometimes AI isn't the best solution. You know, it's very smart and it's an excellent component and tool, but there are processes and certain objectives that are better accomplished using other methodologies. And so out of error control utilizes the broad database and list of various control methodologies so that the best is used for each individual objective. The way that we implement our out of error controls through the Griffin AI toolkit. Inside of here, we can communicate directly with the DCS and the plant system-wide, develop control applications and logic for whatever objective it may be in whatever component, be it cooling towers or steam temperature control, combustion control, etc. And then there's the ability to develop advanced AI or more traditional regression or empirical models. And there's also some other tools to utilize additional artificial intelligence methodologies through evolutionary algorithms and optimization. And so I'm a very results driven and oriented person. So that's what I want to focus on primarily here and discuss with you what those results are. So we implement our system through a no-code development platform, meaning that it's very easy to interface with, very easy to interact and develop new control in response to, in the moment, recommendations from operators and engineers. There's a lot of AI components inside of here, such as neural networks, which are very capable of learning a process from operational data over time. The system learns to very closely, if not nearly perfectly, represent a process, depending on the complexity of the process, of course. All this is done using immediately available data in real time. And then we use evolutionary algorithms and different methods of optimization so that we can identify the best operating conditions to realize whatever objective it may be. This essentially takes a million different guesses, this particle swarm optimization, at what optimality looks like, tests it, and then decides what truly is optimal to find the minimum, the global minimum of a process and in its current state. Everything that we do bases itself off the DCS curve so that it's reliable, it's robust, there's no hesitancy or worry about the process drifting into an unsafe or unreliable location. And it interacts directly with the DCS. There's an opportunity for operators to turn the AI optimization system on or off if it's active. Griffin optimizes a process, calculates what the best set point should be, determines the bias based off of the DCS's unbiased demand, and then sends that bias into the system, effectively realizing closed loop control using these biases. And one other key thing is that our system resides completely within the network of the DCS so that there's no outside communication, so that there's no worries about cybersecurity or other issues like that. Everything's inside of the DCS's own network, so there's no issues or concerns there. So now we've been able to apply these systems at a large number of different facilities and units, in total about 23 different units, 15 tangentially fired or corner fired units anywhere from 300 to 800 megawatts, some 4-corner, some 8-corner units. And then we've also done a large number of wall fired units as well, single wall and opposed wall fired units, similarly sized applications. Very quickly, just a brief history. Really, we've been doing this over the past 8 years. All of these are closed loop control, meaning that the operator simply turns the system on and it's optimizing from there on out. It's determining the optimal operational parameters, and without the operator having to do anything else, it's controlling the unit within a range of control around the DCS curves. As I mentioned, we've been doing this about 8 years at a multitude of different size boilers and different configurations, all with many different DCS systems. And that's another important feature of this application, is that it's DCS agnostic. It can really interface with ABB or Foxborough or Emerson, any of these different vendors that exist out there. And then a short history as well of our wall-fired solutions. Some results here. First, we'll talk about a site where we've applied together work for emission rates, heat rates, temperature control, and system degradation. So first, emissions. What you see here is quarterly averages across the unit's load range of emission rate. When we began, this dark green line, towards the close of our project, this is over 2 years of the system self-learning, self-adapting itself as more operational data is achieved and collected. In total, about a 23% decrease across the entire unit's load range, from minimum load 25% of maximum capacity to 100% capacity. The other key thing here is the system had a service factor of over 85%, meaning that it's doing this nearly all the time. An example of an on-off test, the system was off over here on the left side of the graph for about 12 hours. Then when the Griffin system is activated, almost immediately within an hour, NOx is decreased by 15% for a similar load, with no real detrimental effect to other parameters such as CO. And then we look at a total of 6 months, 3 months of analysis on the left and on the right. About 8.5% decrease during this quarter, these 3 months, 12.5% decrease in NOx during these later 3 months here. And then another key thing that was possible here was the fact that the system was able to realize NOx emission rates that had never been realized before by operators or anybody else running the unit. The optimization system in Griffin systems capable of finding new configurations to outperform anything that's been seen previously in the historical data. Now then, if we look at tube metal degradation inside of the system due to high metal temperatures, see that before intelligent control was initiated, we see over the time span of about a month, 257 instances of high tube metal temperatures above this solid black line here. After advanced control, a little bit more active parameter, control parameter down here in the purple, we see that over an 80% decrease in the number of instances of high tube metal temperatures, representing greater tube life inside of the unit. One other capability we've been able to do is identify tube leaks far earlier than able to do so traditionally. And we do this using advanced dimensionality reduction tools and process analysis. These signals here are what the plant looks like over 3 days. Very messy signals for these different load swings. What our tools do is they break this information apart into very easily identifiable regimes, recognizing that here, this is normal operation. Here, likely the tube had a pinhole leak, was starting to get close to erupting and failing. And in the red, you see it's an entirely different operating regime, meaning that these parameters indicate something's happened inside of the unit, which was a tube leak. So almost 12 hours before the unit actually identified the failure and come offline, able to know that there was a problem long before operations would have traditionally. Beyond that, at this same site, able to do cooling tower optimization in this application. The objective of reducing auxiliary power usage. See in this example, by adjusting the fan speeds of individual cells in this cooling tower, this is a forced draft cooling tower, it will reduce auxiliary power usage by over 5%. It's just a summary of those different advantages and results at this single site. And that's a key thing here, is that these are synergized optimization objectives. These are all working congruently in parallel with one another to see all of these benefits on a single system. That's the out-of-variant control benefit right there. Multiple gains across the process. Very quickly, I'll talk a little bit about heat rate as well. Able to see improvements in overall heat rate on average in the range of 0.4 to 0.7% through just combustion optimization. See as high as 3% in individual observations, but on average about that 0.4 to 0.7% range. In another project we've done, able to see similar results in actually minimizing heat rate itself across the load range. On average, about 1 to 1.5% reduction in heat rate here through, again, simply combustion optimization. When you factor in components like SIP blowing and cooling tower optimization, all those other features, that heat rate benefit increases. Another application that we've done is managing mercury emissions and also pack injection to control mercury emissions. What we were able to see is that pack has a detrimental effect on other portions of the process, particularly opacity measurements at the stack. Through advanced control, we're actually able to lower the pack injection rate, which is shown by this average, this brown line compared to this blue line, while seeing lower mercury emissions and lower on average opacity and decreasing opacity alarms by over 95%. All of this through that adavariant control, applying the right control methodology to the right process, really keying in on the knowledge of the process. One thing that we strive to always do is gather knowledge from operations and engineers and develop that directly into our systems. Finally, another key thing we've done is the ability to predict coal quality in real time using operational parameters. See that by doing this at a particular site using readily available boiler, scrubber, and feeder data, able to predict what the coal quality is like and able to improve our predictions of unit operation and emission rates by over 40%. So drastic improvement in predictability and understanding of the unit and what kind of coal is being burned and how that affects the entire process. So in conclusion, wrap up very quickly, DCS control is meant to be safety oriented. That's really what it's the best at. Doing advanced controls inside of there is usually time consuming and expensive. That's really where adavariant control shines. That's its main purpose, is that flexible, agile layer to do intelligent control. Machine learning and AI is important, but that's not the only solution approach. It's important to use the merits of the process itself and to determine how you implement that control. And the toolkit framework, such as the Griffin AI toolkit, is really the best way to do that. In our case studies we've discussed, we see multiple benefits across different portions and processes within the system itself, decreasing a bunch of different objectives that we had. And then finally, as you stack different operational objectives, moving from simply combustion optimization to including knowledge-based SIP blowing, intelligent SIP blowing, and then also when you add in optimization of cooling towers, fan usage, and other components across the system, you see that those savings increase dramatically. This chart has been generated using about $100 per ton, metric ton coal, US dollars, and a plant service factor of 95%. You can see as high as nearly $6 million saved through these very simple digital solutions applied to a system. So thank you all for your time. Yes. Is there a comment? Mr. Pangsha.
Pankaj sir, you're on mute.
Oh, I'm sorry, that was a little muffled.
Thank you, Mr. Jacob. It has been a very comprehensive, process model which you have described and which you have implemented at so many plants. And it's a very good approach, to have the subsystem based, process optimization controls. And I mean, the AI based expertise to be involved in that. And that is a thing which is going to be there for a long time and serve the Indian power plants for the objectives they are striving for. Thank you so much.
You're very welcome. Thank you. And let me just once again say thanks to CII and all of you for attending. Very much appreciate the opportunity. Thank you.
Thank you, sir. Now that Mr. Rajesh Kumar, who was to talk on digitalization initiatives at Nava Power Limited, will not be able to make it because of certain, problem at their end. So they will not be able to join. But now we have Mr. Elisha from the Olive Stone. He's the sales director there, and he's going to talk on cyber security. In fact, he was supposed to talk yesterday, but he could not make it because of certain reasons. But today, you are welcome, sir. And I hand over to you. Please go ahead on your talk. Cyber security, as such, you know, is a very, very, very important issue because now we are talking about the digitalization and then a lot of data sharing with the external agencies and within the plant. So it has to be ensured that the security is very important, and no external or internal, leakages should be there on that. So I invite you to talk on this issue. Mr. Elisha, please.
Thank you, sir. Thank you,
Welcome.
sir. Thank you for the invitation and for the opportunity to speak with you all today. I think the previous session was actually an interesting introduction because I would like to focus exactly on everything that's going on inside the DCS and all these OT operations and how we can maintain the separation and security of these OT operations while still having the data that's being generated, that good digital data, the good analysis, and bring it out to the enterprise side and doing so safely. I'll make one other comment before I start. I have my video on now, but I am from home. I have one son here on Minecraft, another son on Spotify. So if the bandwidth starts to get poor and you can't hear me properly, I'll turn off my video. So please let me know if that's the case.
Surely, sir.
So just quickly about my company. So my company's name is Waterfall Security. I'm a sales director in charge of parts of Asia, including India. We were founded in 2007. We're based in Israel. We have offices around the world, including here in Israel, the USA, in Europe, in Abu Dhabi, as well as in Singapore. We are exploring perhaps within next year opening an office as well in India and in Korea. We have installations in thousands of different industrial sites all around the world. And if we think about power specifically, power is definitely Waterfall's #1 vertical. The company was started with the focus on power generation, nuclear and conventional power generation. In the United States, in Japan, in Singapore, in Israel, in many other countries, well over 50 to 60% of the power sites in each of those countries that I mentioned are using Waterfall security technology to protect their sites. In India, we do have several customers today. Some of these were brought to us through our global OEM partnerships. So sadly, I'm not able to mention any of the specific end user names, but if we want to discuss, anyone's interested to discuss offline, I can mention a few references. So as I mentioned before, our topic today is industrial cybersecurity, and our challenge is really this OT IT problem that has been the focus and the challenge of many power generation companies for many, many years. Of course, we have all the great digital data that's being generated on the OT side. Some of the sites that exist out in the world today, and in India, I know, have been around for so long. They were never built with the internet in mind. They were never built with cybersecurity from the internet as a core issue to make sure that we overcome. The digital data that's being generated on the OT side is giving us monitoring capabilities, giving us visibility to the business side. It's giving us predictive maintenance, like we heard before. And we really need that data to come out from the OT to the IT side, to the corporate enterprise side, so that we can maintain business continuity. And of course, once we are connecting the OT network to the IT network, we are exposing the OT network to the enterprise with the internet. Now, of course, we are exposing the OT to all these potential cyber attacks. So how do we maintain these two challenges together? How do we maintain the continuity of our business, the visibility of the OT network, while still giving absolute protection of the OT network for the internet-based attacks? This is our challenge. This is what we are trying to accomplish here. So when we talk about industrial cybersecurity, we'd like to break it down to 3 important rules that we must follow, and from there, we'll try and develop our solution. Rule number one that we need to always keep in mind is there's no such thing as 100% industrial cybersecurity. It's just not possible. It's a myth. If any vendor, if any consultant comes and tells you, all you need to do is XYZ, install this product, install this tool, then you are protected. It's just a lie. It's not possible. There are so many ways an attacker can come to the network, external and internal and human-based attacks, etc. There are so many things that they are trying to do. You cannot simply implement one technology, one strategy, one tool and say, now I am complete, now I'm covered. I don't need this tool or that tool or my cyber team. So we must always be vigilant, and we must have many layers of cybersecurity protection. Rule number two is that anything that is software-based is inherently hackable. We cannot rely purely on software tools. Human beings write code, human being makes mistakes, there are bugs in code. If we are relying purely on code written by human beings with bugs, we know we will be attacked. The attackers today are smart enough to analyze those software tools, find the holes, and leverage them into their own cyber attacks. So we know this to be true. Any attack you've ever read about has been the penetration of a firewall. And at the end of the day, that's all a firewall is. It's a software tool. We think about it as hardware because it's sitting there on that server, but at the end of the day, it's software. You look at the websites of Check Point and Cisco and Fortinet and all the leading industrial firewall vendors, they list on their website their known vulnerabilities. They list on their website the things that they are aware of, the bugs they're aware of, and the patches that they're constantly putting out. And this doesn't even cover the zero-day attacks that they themselves haven't become aware of yet. So we know we cannot rely purely on software. And rule number three is that anything that is, anytime there is an attack, it's because a piece of information has come into your network that should not have been there in the first place. That's what the attack is. It's something penetrated into your network, which is the ransomware, the virus, whatever it is, something came into your network. And if we are relying on firewalls, which at the end of the day are software-based networking tools, which are doing bi-directional communication, which are bringing data back and forth with TCP/IP acknowledgements, then we are essentially opening the door to our attackers. We actually do at Waterfall an entire presentation simply pointing out some of the inherent problems that exist within firewalls. Because at the end of the day, as I mentioned, firewalls are routers, they're network forwarding tools. That's what they're doing. They're taking messages from A, sending it to B, and getting an acknowledgement back to A. And it doesn't take a very sophisticated attacker to leverage on top of those TCP/IP channels and push his attack in. And there are many different ways that an attacker can not only overcome a firewall, but actually leverage the firewall and use it as his method of attack. So we're not saying that firewalls don't have their place. Of course they do. They are a core component of the overall security architecture and all the tools that we're trying to implement, network segmentation, etc. It's what essentially the IT security tools are based on and built on, and that's the foundation. But things like intrusion detection and updates and patches, these are all IT methodologies and IT processes which aren't actually designed from the ICS perspective. They're not designed to protect the OT, the DCS, the SCADA. And those networks, everything that exists over there, they were never designed with security first in mind. You think about a PLC was never designed with security as its focus. How many PLCs exist today which have encryption on them, which are actually talking to the HMI with encryption to make sure that someone can't leverage an HMI and use it to manipulate what's going to happen from the PLC perspective. Of course, it's rare to ever find anything like that because they weren't built with those goals in mind. So we need a different approach when we're talking about protection of the OT network. I'll take you through one of the most famous use cases, which is the Petro Rabbi attack from 2017 in Saudi Arabia. This is just a very kind of crude look at what their architecture is over there. They have a very simple Purdue model with their OT network from layer 2 and down, a DMZ there in the middle with a firewall, and layer 3 and 4 and out with a VPN connection. That firewall with the DMZ, it actually turned out, as I mentioned before, not only was it not protection, it became the leverage how the attacker managed to get in. The attacker was able to gain credentials of a VPN, and because he was on the VPN, the firewall recognized him. The firewall said, oh, I know you. You're fine. You can come right in. And once he was past that DMZ firewall, he was inside the OT network. They were able to deploy their malware on the workstations of layer 2. They're able to install their code and control the PLCs. And from there, they were able to take down the safety systems on the plant floor itself. And the reason why this attack is so discussed is because that firewall, at the end of the day, became a green light. It became not only, as I mentioned, not only the no protection, but allowed the attacker to come right in. And the attacker, by disabling the safety systems, had the ability to actually harm human life. They had the ability to actually create an explosion by disabling the safety systems and literally kill people that were there. Generally, when we talk about attacks, we think about, shutting down production and things like that. This attack is most famous because the safety systems themselves were actually targeted. People talk about air gaps, of course. You think, well, I have my firewall, my DMZ, I have my air gaps in there. We need to make sure that we are talking about the right terminology. There's a huge difference when we talk about a firewall and we talk about DMZs. We talk about a DMZ with zero routable connectivity or all connectivity being taken away. If we have some routable connectivity, if there is some connectivity there whatsoever at all, then you don't really have a pure DMZ. You don't have a pure air gap. We need to make sure that when we are talking about an air gap, we are not simply putting a networking device on one end and a networking device on the other end, and then saying, because of this kind of physical, mental barrier separation, now I will not have any connectivity. This is absolutely not providing protection. Anytime there is TCP IP connectivity, it doesn't matter how many hops you need to go through. If a sophisticated attacker is trying to get in, they will be able to get in. They can pivot from one device to another very, very simply. So we need to be very careful when we talk about these types of tools. You talk about gaining budgetary funding for a DMZ from your CEO, and he provides it to you, and then you come back and you say, well, actually, what we need to do now is X, Y, Z. So, well, you told me you put in the air gap. So we need to be very clear on what it is we're trying to accomplish and how we're accomplishing it. I'll take you through one of the most common scenarios that we see in our day-to-day with our power generation customers. It's, I would say, our most popular scenario that we have with our customers, certainly in power generation, is the use of OPC. We have all the DCS, we have the PLC. Generally speaking, there's going to be an OPC server there on the edge of the OT network that's consume its layer 3, maybe layer 3.5, which is generating OPC data, which is then feeding into Historian, which is now talking and being used by the IT and the enterprise side. Again, if we assume that the Historian is an OPC client, which is reaching through to the DMZ firewall to the OPC server, so now again, we've created this OPC TCP-based tunnel going through a DMZ firewall. So what are the ways in which an attacker can leverage that for their own attack? Well, if you are understand the basics, which I pretty much only understand the basics, let's say, of OPC, but OPC DA is a Windows-based tool. It's a Windows-based protocol. It requires DCOMs. So if we're using a Windows-based server and we understand the tools that exist there, we can execute our remote code and use that to leverage and gain control of that OPC Windows server. And from there, you can pivot out to the PLCs and to the other controllers inside the OT network. Additionally, you can send in write requests from the outside to the OPC server itself. If you have access to the server, you can send in requests, and that can actually manipulate and destroy data on the OPC server, which would be ruining your business and ruining the data that you are doing for your analysis on the Historian side. And finally, just simply based on the DCOMs, if you are running DCOMs through your firewall, you're not left with a firewall. At the end of the day, you're pretty much left with a very large holes and gaps in your firewall, essentially turning it to Swiss cheese, saying that the firewall at this point is not really accomplishing much of anything. So we need to be very, very aware and careful of the tools that we're using in our OT network and accessing them from our IT network and how we are going to provide protection. It's very common that we'll see tools that customers will put in place to make their lives easier from a process side and engineering side will entirely ruin their entire cybersecurity architecture. The waterfall solution to these problems is what we call the unidirectional security gateway. This is providing absolute protection of the OT network. I'll explain to you how it works. From here, maybe I'll talk about one or two use cases, one or two examples that we have, and then I'll be happy to take questions. You have here on the screen, on the left-hand side would be the typical OT network, industrial. On the right-hand side, typical IT. Let's assume that everything here in the red box is sitting where the DMZ firewall is sitting essentially today, layer 3.5, give or take. Everything here in the red square is the waterfall technology. It's a combination of hardware and software. The goal here is to take the data from the OT network in a unidirectional manner, bringing it out to the IT network and ensuring that nothing can come back that would harm into the OT network. We want nothing coming into the OT network at all. So the hardware component is the gateway you see here sitting here in the middle. It consists of two important modules, the TX transmission module, which is a laser. We are taking data, sending it down a fiber optic cable, and it's received on a photocell on the IT side. Because there is no laser transmission on the IT side of the device, and there is no receiving module, photocell on the OT side of the device, it is physically impossible for data to come through this device from the IT side to the OT. It is only literally physically possible, based on the laws of physics, for data to pass in a unidirectional manner down the fiber optic cable with a laser and a photocell from the OT side to the IT side, the TX to the RX. The TX sends data to the RX blindly. There is no TCP/IP communication coming back, acknowledgement to the TX. Instead, we are the proxy from our TX host to the industrial system, creating a bidirectional protocol communication session over here. We are the proxy. We bring that through the gateway in a unidirectional manner, and we recreate that bidirectional session acting as a proxy again on the far side. No attacker. Yes, please.
Alicia, if you can conclude in a minute or two.
No worries. I'll finish with this slide and happy to take any questions. No attacker in the history of the world has ever managed to penetrate and break the laws of physics. So what we are accomplishing here is 100% physical protection of the OT network. Our software is sitting on these host servers, and this is what's giving you access to the industrial systems. So as I mentioned before, if we're talking about OPC, we're talking about a historian, we're talking about a database, Waterfall develops literally hundreds of different software licenses, which give you the ability to pull and take the data from the industrial server on the OT side and create a replica copy of that server for your access and use on the IT side. This is what Waterfall is trying to accomplish, to give you access to the data in real time, but have unidirectional protection of the OT network so that there is never, ever going to be an internet-based cyber attack into the OT. Of course, we can talk much more about this topic specifically and cybersecurity in general. I invite anyone that's interested to get in touch with myself or our local partner in India. We'll be happy to continue the discussion, show you a demonstration, arrange for a POC if you're interested, and certainly continue this discussion. So thank you everyone for your attention, and thank you to the Institute here for arranging this entire session today. Thank you.
Thank you, Mr. Alisha. It was a very, elaborated overview of the things which can go wrong and how they can be, secured. And it's a very hot topic today, and is a very much a need today. And we'll have the questions just at the end of the session. And
Sure.
I request participants to put their questions on the chat box so that they can be taken up after that. Thank you, sir.
Thank you.
Now that I invite Mr. Kaustav Day, he is Manager IoT at Toshiba JSW Power Systems. He's going to talk on digitalization of the thermal power plant. So, Mr. Kaustav.
Thank you, Mr. Pankaj.
Welcome.
And also thank you, CII, to giving us opportunity to share our solutions for the digitization of the thermal power plants. Let me share the screen first.
Just a minute, Mr. Kostov. It will just come up in a minute for you. Share button will activate.
Okay.
Yeah, it is activated now. Yeah.
Okay. Thank you. So today's my contents of the presentations are like first is I'll give some high overview of our company's profile. Then I will come to the Toshiba's IoT enterprise IoT reference architecture, features of IoT platform, APR and its concept, and our RMDC, remote monitoring and diagnostic centers experience. As we are in Toshiba's, our head office is at Japan. So we are not only in energy domains, we are also present in the infrastructure systems, building solutions, retail and printing solutions, electronic devices and storage solutions, digital solutions, and battery businesses. As we belong from the Toshiba JSW Power Systems, we have a factory in Chennai, and our engineering office is at Gurgaon. The factory set up on 2008 and engineering office set up in 2009. So Toshiba is present in the business area design, engineering, procurement, manufacturing, sales, construction, commissioning, and service provision. So TJPS also mark his footprint in the IoT or cyber physical solutions, which we are providing along with our headquarters. So in our factory, we have a large scale of manufacturing of steam turbine and generators, which ranging from 150 megawatt to 1000 megawatt, which can cater critical, supercritical, and ultra supercritical units. So we can do in our factory procurement, fabrication, welding, assembly and testing, and shipment also. Now I come to the main topic, the Toshiba's IoT technology enterprise and the reference architecture. So basically, in the IoT enterprise, there are two worlds in the present systems. One is the physical, another one is cyber. So in the physical world is the data world, where the data will be sensed and it will be recognized in the cyber world. In the cyber world, it will be analyzed, predict, and optimized. And further, after optimization, the control philosophy will be developed, and it will go to the physical world to make a new control philosophy of the equipment. So we are present, as we have mentioned, that we are present in the various domain: power chain, T&D, building, office, industrial, transportation, device and storage, information and communication, automobile, logistics, and medical. In this particular presentation, I will majorly concentrate on the power generation systems. Toshiba's IoT infrastructure based on the two major infrastructure model. One is NIST, National Institute of Standards and Technology, and another one is the IIC. Well, on top of that, along with that, our Toshiba's own R&D technology, which is supporting with the continuous study on AI and its applications by sensor data processing, voice recognition, image processing, statistical processing. So those are along with helping this creating the model. So according after then we are creating kind of a Toshiba's IoT's reference architecture. And as a service, we are providing to Toshiba's digital energy, digital infrastructure, digital logistics, or digital manufacturing. We have a kind of a three-tier of architecture. One is edge, another one is platform, another one is enterprise. In edge level, we are doing the control. So with the communication, edge analytics, transformation sense. Platform, we likely to mean that there is a data lake platform. There will be the analytics platform, and there might be also operations platform. So in data lake, we are using like a kind of a master data lake, or this is data lake. Analytics, we are using the big data analysis, machine learning models, operations like monitor and diagnosis management. As an enterprise level services, also it can be integrated like a ERP, CRM, or maybe SAPs, API, UI, Open APIs, UI. So all these enterprise level services also can be integrated in the Toshiba's IoT reference architectures. So basically, our aim in this architecture is control and service. So I like to come to the features of our IoT platform. So in our IoT platform, there are two stages. One is the platform, another one is where the applications are belongs. In the platform, there is a data link framework and HMI framework, and along with that, there is a distributed database. They're like engineering database, plant operation database, outage report database, asset database, as equipment maintenance. So any kind of database we can integrate with the system, but all the databases will be like in the distributed platform. It will be not in a single platform we are going to integrate. It will be in a different distributed platform, and we will integrate the database for the different kind of applications. Our applications like a digital twin, which is basically for the performance analysis, failure prediction. It's nothing but APR. I will describe something more on this failure APR in the for coming slides. Next one is the operational improvement like turbine quick run-up system, boiler combustion, blower optimization system, asset management system. Next one is the field work remote assistance on the document access, in knowledge transfer, also the cyber security. In the dashboard, also we have a kind of these all the service levels are in a plant level service level, and the top of that, in case of the enterprise level service level, like a dashboard for the senior manager of the corporate level people, and or also there is a solution for the fleet operation, the optimized load distribution for the different units. So I first will describe about the different features of our different platforms. So we have platforms features are like selectable microservices, hybrid configurations, distributed database, open APIs for external system linkages, and data access for the information model. So I will come describe one by one. So for selectable microservices as per database is as per customer needs. So some customer needs only one services, might be the digital twin or might be the failure prediction. Maybe the customer aim is to improve the outages or might be the improve the hit rate. So according to the customer requirement, we can select the particular microservices, and we can select that particular database, and we can create the model for the particular. If there is a if customer wants the linking of the database for their failure prediction with the digital twin or might be the operational improvement, that also can be possible. We can integrate all the different models and database together. Next is the hybrid configuration. So in the hybrid configuration in the platform, we can provide our solutions in the on-premises platform as on-premises platform, also in the cloud-based platform. So in the on-premises platform, all the IoT racks, all the IoT softwares, it will be belongs to the plant level, where the DCS data will be collected from the DCS, and it will be all the everything will be at the plant level. But we can do also provide our solutions at the cloud platform. In the cloud platform, all our solutions or services can be provided at the belongs at the cloud level. So where the customer corporate offices or customer other locations can also monitor access the same cloud and monitor the plant's data or the plant particular solutions. Also, Toshiba, we have kind of RMDC services. We can also monitor that the cloud platform and support the customer as required, as per need. Next platform features is the distributed database. So the first there was initially there was a traditional platform we call like a integrated platform, where all the databases has been integrated, and from the integrated databases all services are linked. But as today's but there is a problem is that in case of integrated database, it is easier to link, but it is very difficult to maintain. The maintenance is very difficult. So now we are coming with the distributed database. So in the case of distributed database, all the database for individual solutions or individual services will be different. However, all the solutions and services can be interlinked with the open APIs. The feature 4 of this platform is that the open APIs of the external system linkages. So there might be there are several open APIs available. Might be customer who wants to integrate any kind of any other open APIs, like some customers, if we are going for a prediction of the renewable energy forecasting, or might be so there might be the weather predictions open API, or might be any other open APIs. If customers wants to integrate with the IoT platform, that also can be possible. So that is another features. We can integrate any of the other open APIs of the third parties or customers in our particular solutions, and make our and provide the necessary support to the customer. And the fifth one is the data access by the information model. So there is a kind of a model which is where the sparse data and the information on the equipment. Suppose if there is if customers want to get information for a particular equipment, just a single click, that also can be possible. So suppose there is a pump, and if any customer wants to just click on a pump and wants to see that the history of pump maintenance, history of the pump particular specification data, might be the pump operating parameters when pump was get failure. So any kind of data can be linked with a kind of a single click. So this is a kind of a overall image of our IoT platform. So in the plant level, I already described that there is a information management, engineering data, data utilization, and on-site support services, which are interlinked, which are linked, and also we can link with that API. And finally, all this information model is integrated with the optimal integration for the power generation. Also, these solutions can be integrated for the use of augmented reality or virtual reality platform, or maybe it can be the HMI that allows the data access in line with the human thoughts. So according to this can be the all kind of solutions can be integrated, and it can be provided complete comprehensive solutions for the customer. So as we are mentioning, we are not only provide solutions for only for the thermal energy, we are also providing solutions for the nuclear, renewable, hydrogen, and electricity distributions also. So now I come to the APR. APR means advanced pattern recognition and its concept. So in case of APR solutions, this is basically advanced pattern. In case of any equipment's operating pattern got deviated from its normal pattern, it will give us a kind of a abnormality detection. In this abnormality detection is not as similar as like a DCS detection. It's a different. It depends on the correlation based models. And if any abnormality detection appears, then it will intimate to the plant O&M people. Then accordingly, the maintenance work will be support it will require, and then accordingly that the repair work order generation will be there, and then after the repair is repaired, then it will again go into the monitoring mode. So how we prepare this kind of advanced pattern recognition model? So first we select the target. Suppose we have to create the model for like a turbine or maybe HP turbine. So we have to tag the required data or required tag input for that particular equipment. Then we will create history. We'll take the historical data, at least 6 months or 1 year data will capture from the plant, and then we will create the particular equipment model, and then we will then it will be monitored on the real-time basis. In case of real time, if you see in the bottom screen, if you see in the bottom screen, this cyan line is kind of a expected parameter of this particular parameter. It's the expected value, and the yellow line is basically the actual value. In this particular situation, when the yellow line appears from its gray band is basically its operating zone. If it is going above its gray band or its operating zone, then this red line has appeared. Basically, it is kind of a high alert of this particular parameter. But DCS may not be known at this time about this parameter has been deviated, because this model has been created on basis of the correlation with the different parameters of that particular equipment or the particular assets. So if you see as a comparison of the DCS value is a kind of a fixed value. Suppose for a bearing temperature, DCS value is a kind of a fixed fixed value. Suppose 90 degrees centigrade is when you will get the alert at DCS. But this model, if it can give you alert, might be in different situation, different atmospheric condition, different load condition. All this correlation based model, this will give you the okay, this particular parameters has go beyond its operating zone. So this is the beauty of this APR apart from this DCS. So after that, we get that alert. Then there is a kind of a automated diagnostic model or automated root cause analysis. So from this automated diagnostic model, you will get understand that why this alert is appeared. If suppose a bearing temperature high alert is appeared, so from this automated diagnostic model, you can get understood this bearing temperature is go above might be due to the high due to any lubrication issues, might be the cooling water issues. So this kind of root cause, automated root cause analysis is also there. So and there is another process is that the Toshiba, as we are OEM, so we are our subject matter experts is also going to provide the support in case of any critical alerts to the customer, to the particular O&M team. That maybe some of the alert is always not like that. The automated diagnostic model can be give us the can be solved. Suppose a critical vibration issues, so that might be require far more study with that OE subject matter expert. So those kind of support can be provided by us also. So this is like a complete cycle of this APR. In case of any abnormality detection from the normal operating pattern, it will go and analyze the planned document. So this is kind of a root cause analysis, automated diagnostic model. Then accordingly, work order will generate it. Then work planning. Then it will check spares. Then work will be carried out, and then further again it will go to that normal operating zone in the monitoring mode. This is a complete PDCA cycle: plan, do, check, and act. So now I come to our RMDC experience. RMDC is for Remote Monitoring and Diagnostic Center.
Mr. Kostava, if you can conclude a little fast, maybe 1 or 2 minutes.
Yeah, sure. So the RMDC, we have a kind of RMDC center in our Gurgaon engineering office. So in that we provide the continuously 24/7 support. So what is the purpose of the RMDC is that response operational issues as accurately as soon as possible, prevent unplanned outages of equipment or outages with the proactive maintenance and enhancement of equipment life. It also detects the any inefficient operation, might be any heat rate degradation, and increase the efficiency of the plant. So we use two kinds of model: APR, which I have already discussed. Another one is TPMO. It is nothing but it's a thermodynamic model. It's basically used for the heat rate improvement. So this is a typical RMDC scenario where from the plant data will flow to that our RMDC center, and accordingly RMDC workflow will be there. And RMDC again intimate to the plant people to take the necessary actions. So this is a kind of a typical RMDC configuration. If we do the configuration on cloud based, so this is the plant level DCS or Pi server. Then it will be connected with the IoT rack. These all the solutions like historian database or ETA Pro, our solutions, AXView, all this can be part in that the cloud in the cloud level. And now Toshiba also we can also monitor those data through the internet, and customer headquarters also monitor the data. So the key aspects of the RMDC is that we can build asset model for the steam turbine, boiler, fans. So any equipment or any assets of the any thermal power plant or any conventional power plants, and we will monitor all the data 24/7. Continuous basis, all the parameters. So we will notify if any alert appeared. So we will notify to the O&M engineers on timely manner. In also the root cause analysis and the recommended action in case of any alert, we will also guide it with that particular recommended actions. And also, as I described that in case of any detailed investigations required, that also can be supported by our subject matter expert within 24 hours. So in this RMDC, the beauty is that the customer do not has to take any hardware, software, or cloud services. So all those things will be belongs to us. So this is a kind of a typical workflow of this RMDC aspects. So in case of alert, how this workflow will be there, and there is also we'll provide the kind of a monthly report submission. This is how this process, how the alert will be generated, and from the client file system, data will be fetched, and then it processing with the data flow and the deviation alert. Then it will be notified the alert to the site, then discussed among the subject matter expert and submit the RCA, and also the maintenance strategy and actions will be developed. Thermal efficiency also, we are providing daily report to the customer as a thermal efficiency reports. Also the overall generation graph, any root cause and the analysis and the recommended action for the deviation of the thermal heat rate, any heat rate parameters. So I come to the last slide. These are kind of a tangible and intangible benefits of this RMDC services. It will help to improvement in the availability and efficiency, reduction in unscheduled equipment outages, reduction in maintenance cost and generation cost, increased asset utilization, asset extended of equipment life, and identification and correction of underperforming assets. Intangible costs like comparative studies, customer affections, expert advice, and augmentation of O&M skills. Thank you. Thank you, sir.
Thank you, Mr. Costa. It has been a very comprehensive suite which you are providing. We'll have questions at the end, and now we'll proceed on to the last paper of the session. Which is by Mr. Pramod Dalvi. Is Senior Manager at Danfoss Industries. And the talk he's going to talk on is how Danfoss develop reliable and efficient AC drive solutions for power plants. So, Mr. Pramod Dalvi.
Mr. Tavi is on mute.
Yes, sir.
Good afternoon. Yes, sir. Am I audible?
Yeah.
Yeah. And thank you, CII, for giving Danfoss an opportunity to present our reliable and efficient drive solutions, which are commonly called as VFD.
Mr. Pramod, your voice is really feeble. Prabhat sir, is it fine? Pankaj sir, is it fine for you or?
Slightly lower.
Yeah.
Slightly lower. So you can adjust your mic.
Yeah. Is it audible now?
Yes.
Yeah,
Sir.
better.
Perfect. Sir.
Better.
Thank you.
Yeah. So I'll go to the next slide. Just an overview about Danfoss. We are a privately held ownership company and headquartered in Denmark. And if you see the left-hand side, we are 34,000 employees, and worldwide we are operating in 100 plus countries and 70 plus factory sites in more than 20 countries. We work segment-wise. You can see the major segments: Danfoss Power Solutions, Climate Solutions, and Danfoss Drives. And we belong to Danfoss Drives, that is AC Drives. And the percentage we held in our own company is around 23%. Danfoss Drives, just want to share some numbers. We are 1.5 billion euro revenue company with the 27 million drives delivered, and we are operating in 100 partner, 100,000, sorry, 1,000 partner companies, and we have global presence in 100 countries and 50 sales and services offices in 10 factories. We are the first movers in this VFDs from 1968. These are those 10 factories for VFD or AC drives globally. And we are working with the two brands, VLT and Vecon. Danfoss has acquired company named Vecon in 2014, and those factories also belongs to Danfoss. So the blue ones are actually the Vecon factories, and the red ones you will see the Danfoss factories. And important point to be noticed is the India, which is in the last, which is a recent uh, addition in factory in 2014-15. So coming back to the topic, we are talking about the basic applications where the VFDs are being used today, and how Danfoss will is offering efficient and reliable solutions to these applications. So basically, we divide this into two parts. One is power generation, and second is balance of plant. So power generation, boiler and turbine, we see applications like boiler feed pump and then IDFD and PSA fans, circulating pumps, cooling water pumps, air cool condenser. These are the common applications. Then if you come to balance of plant, we have ash handling units and coal handling plants and fuel gas desulfurization, waste to energy, water treatment plants. And the applications within these processes is we see pumps and compressors, apron feeders, stacker reclaimers, long conveyors. So these are the typical applications where we are providing our solutions. And for the operating voltage, we see it is 415 or a 690, or sometimes it goes to 3.3 or a 6.6 kV based on the power rating of the motor. And the configurations where we work in low voltages, we work in 6 pulse, 12 pulse, and active front end. These are the based on the harmonics and the power rating. We define this configuration, and if it is consultant, then we follow the consultant specifications. And then for a medium voltage or a high voltage, it is either 24 or 36 pulse. Recent market trends and technology for these applications, I have divided our presentation into two parts. One is efficiency and the second is reliability based on the topic. So high efficiency is a, a very important feature of our drives, which is 98%, and how we achieve it is through temperature controlled fans and low loss, because using the PWM patterns, and we have specially designed heat sinks and low loss DC reactors is built in. So overall effect, we get around 2% losses, so we can achieve 98% efficiency. And then with this, the customer is benefited with the best of compliance. First is the compliance of IEC, and second is the commercial benefit also. So the next slide will we are just showing one example. If you are having 315 kilowatt 10 drives VFDs in your plant, if it is Danfoss as a supplier, you see the unit loss of 315 kilowatt VFD is around 6.9 kilowatt. So overall 69 kilowatt. But if you take other multinational brands, you see the heat loss is a bit higher, and because of that, the difference of heat loss, if you see in the third column, is around 29, 22, and 45 kilowatt for the same rating. So in an average, for those competitors, additionally, an end user has to pay an extra energy bills of 11 lakhs or 8.5 lakhs or 17 lakhs. So this is where the low loss is very, very vital, because this is just we have taken an example of 10 drives, but if you have 100 VFDs in your plant, just imagine what is the impact on the end user. The next slide is talking about intelligent heat management. Again, it is a part of efficiency. So we have cooling fans which can be easily cleaned, because normally the fans are getting the the dust or moisture. So this is one point where we are standing out from the competition. We have panel through mounting where heatsink can be mounted outside. So there also you can reduce the losses. And then we have a duct cooling. This is a unique feature of Danfoss where 85% of the heat we can keep it, take it outside from the control room, and then balance 15% only is your HVAC needs. So next slide we'll talk about more. So this is how you see the pictures of this unique back channel cooling concept. Will take the heat away from the room, and typically we have just put example of a 160 kilowatt drive, and the calculation says that with this back channel cooling you can save almost 41,000, that is around 15% of the your capex investment in the drive. So this is very, very important, and energy efficiency feature for Danfoss. These are the pictures how this back channel cooling is implemented in real life. You can see the duct. We can take this fresh air from bottom in, top out, or back in, top out, or back in, back out. All this is possible with our designs. Coming back to the connectivity, again, this is where wireless communication is. We are having an LCP 103, we call it, which is a wireless local control panel, which has a built-in memory of 16 MB, Wi-Fi speed. Can have a communication through this. Same point where we are saying that we can connect this through a My Drive connect through as it's an app. So you get all your VFD data in this app through this connect. Again, on the field bus, we are independent of all the field bus. It is, you name it, Profibus, Profinet, DeviceNet, CanOpen. You can connect our drive to any of this field bus. As well, you can also connect this drives to any motor. Like today, it is an induction motor, but tomorrow, if you want to change it to, synchronous motor or copper rotor motor, so this is possible. You don't need to change the drive. Only thing you have to, change few parameters. That's it. So this is where we are motor and field bus independent. We can connect to any motor and any field bus. On the low noise operation, see the EMC filters and RFI filters are built in this VFD. So we for a longer length, more than 150 meters, or for beyond that also, we have a dedicated RFI filters are built in. This is where I think we are more successful in where the long motor scenario, when the motor and VFD cables are long, filters are built in. This unfiltered AC drives will produce the electromagnetic interference, which will cause negative impact on the sensitive equipment. So this is built in our. Coming back to reliability part, the IP protection is the one where we have invested up to IP54 and 55, up to high rating, up to 1 megawatt rating. We have IP54 drives. Then on the operating temperature also, our drives are there designed for 50 degrees. Then definitely it saves avoiding, because the chokes are built in, so no additional AC chokes are required. This is the unique feature of Danfoss drive, where these drives were launched in 2004 or 5. The way back of 15, 16 years, we have invested into 3C3 coating as a built-in. and which is complying to IEC 6073-71-3, where the stringent, we just taking an example, if the various gases which are present in the atmosphere, like the example we are taking chlorine, if it is a 3C2 coated drive and the 3C3 coated drives, there is a protection for almost 30%. So many of our competition is working on basic 3C1 or 3C2 protection, which is not helping in the environment where the gases like sulfur dioxide or hydrogen sulfide or chlorine is present. So all our drives will come 3C3 coated by default. And this is a feature of a Vacon drive, which is what basically done in as a engineering, that we can parallel up to 4 number of drives to make a high power rating. For example, if we are working on a 1 megawatt motor, you can always make 4 numbers of 250 kilowatt drives parallel, and they will work in a sync. And in case of one module fails, the drive or the motor doesn't stop, it will run on a reduced load. So this is very important engineering feature, where for the critical applications of ID fan example or a boiler feed pump example, where we cannot afford to lose the downtime, there we can engineer it as a modular concept, and where we can size the 3 drives for a BKW, and if the fourth module fails, this is the it will not stop. The application will not stop. It will run on a BKW load. So this is very popular in cement and metal industries, and it is picking up in the power industry or power plants as well. And we have number of install base in cement and metal industry, and we started this in power industry. This is a picture of Danfoss India factory, which is located in Chennai, Orgadam, which is a 50-acre campus. And in 2014-15, we have invested more than 500 crores. And this is one roof. All the 3 divisions which I have showed in the initial slide are for the Danfoss India is in this campus. It is first lead platinum rated campus. We have our own 1 megawatt solar plant and our own STP, and we are totally independent campus. We have full value chain in our Chennai campus. We have our own R&D, sales, marketing, manufacturing, and supply chain in this campus. Additionally, we have invested into environment simulation chambers, which will simulate -25 to +70. Also, the various certifications you can see. This is an interesting investment we have done, and because of this, we have got a lot of preference from the PSUs, basically from NTPC, EL, or Becon, or BHL. This is load test facility or a type test facility. So we have the load test facility up to 1 megawatt in our campus with 415 as well as 690, and with an active front end generator backup. So we can type test each and every project before sending out to the field. That means your commissioning time is reduced. Plus we have an EMC test. This is upcoming topic now, that the drives, that the VFD is a switching device. They generate harmonics. So because of those harmonics, maybe other sensitive equipments can malfunction. Those areas, the EMC's test or type test is getting mandatory. So we have our own setup there. Then brake test is also available up to 700 kilo. So if you see here, we have all the certification. We are operating into various segments. In a heavy industry, we operate cement, metal, oil and gas, and power generation as a focus segment. And then we are definitely operating on our other segment like HVAC, food and beverage, textile, etc. Yes, as a product company, we must ensure the service support. So we have 24/7 service support across India. We have unique CSC customer service center where customer can log in the data and he can get the update every uh, 24 hours, 48 hours. The automatic escalation also happens. And then we have a Drive Pro unit where we have this kind of a program where we can send the data on the preventive maintenance or offer AMCs, life cycle management is a basic module.
Mr. Pramod, if you can conclude.
Yeah, I think this is the last slide. So in a summary, we are a strong number 2 company in globally as well in India with a strong 18% market share. We have 50 years of drives and application expertise, more than 23 million drives across industries already installed. And a proven, we are a proven reliable partner for 20 years here. We are having one center of excellence, which is a project execution and critical application support. Such we have 5 COEs, we call it, across the globe, and we have India, one of them. With the strong commitment of 500 crore and investment of 1,000 employees, we are serving this market. Again, 24/7 is our service support, life cycle management, and low cost ownership. So that is the end of.
Thank you, Mr. Dalvi. It has been a very informative, talk on the AC drives and all aspects, including the service support and the reliability and the diagnostics you have covered in that. And hopefully the participants will be benefited out of it. Now that we come to the end of the session, we had a very good talk on the digital twin technology, the AI-based solutions, and the digitalization of the power plants, the scope, and the various, solutions based for the diagnostics, process control, and the optimization solutions. So by different, speakers. So we have a few questions which we will pass on to the speakers, and we request them to respond to that, and which will be communicated to all the participants by CII setup. So with that, I conclude the session and thank all the speakers and the participants for this session. Thank you very much. Mr. Mehul.
Yeah, thank you everyone. Thank you speakers. Thank you our session chair Pankaj Bharatia sir for joining us for the session. So now we will take a lunch break. We have exceeded in fact by 7-8 minutes, but we will join back by 2:45 when our next session starts. The next session again is really interesting. Please do join us on time. We have O&M best practices for Indian power plants. Some really good presentations there. Thank you. Thank you. With this, we can close this session.
Okay.
Thank you, sir. Thank you.
Right, sir. Thank you.
Thank you.